In the last video, we went over how to spawn new threads and how to pass data by transferring ownership of a variable from our main thread into our secondary thread. But what if we wanted to get data out of our secondary threads? And something like this diagram, that, my friends, is where thread channels come into play. Let's say we're making some multi-threaded web server. This is our web server here, right? Multi-threaded web server. And we have a couple of threads that are acting as our session workers here. For each session, we might want to log each request to a log file. Writing to disk is a slow process, and we don't want one thread overwriting another thread's log and introducing race conditions and whatnot. So what a good approach to this might be is to introduce a logger thread here that takes all incoming logs and writes them to our log file. This also helps serve our sessions faster since our session that should be B, since our session threads aren't blocked by having to write to disk. Instead, of all of our disk activity is handled by a logger thread here. This is a moment where Rust shines, and the ownership system plays very elegantly when it comes to sharing data from threads that produce data, like our ABC here, to a thread that consumes data, like our logger thread here. What we can do is literally transfer ownership of this data to our logger thread through the power of a multi-producer single consumer channel. That's what this is. We have multiple producers. A, B, and C are producing data that might need to be written to a log, and our log is consuming that data. Because ownership is enforced across threads, these producer and consumer channels lay the foundation for writing not only memory safe code, but thread safe code. Out of the gate, we're able to write code that is pretty easy to understand, and the concept of a channel is pretty easy to wrap your head around, and is less prone to multi-threaded programming bugs like deadlocks and race conditions. We're going to make this even simpler to start with and have a single producer and consumer. It's going to look something like this. We're going to start with a single consumer thread. This is going to be our thread A, or our main thread actually. And we're going to create a channel. And inside of the channel, there's going to be an RX, or a receiving end, and a transmit or TX side of the channel. These are instances that are given to us by the channel. And what we're going to do after we have this channel ready to go, and again, transmit, the TX, is going to be responsible for sending data into the channel, and RX is going to be responsible for getting data out of the channel. So what we're going to do is, with my fancy animation here, we're going to spawn a separate thread, right? And when we spawn this thread, we're going to also, like we went in the last video, pass ownership with, oh, that's egregious, but we're going to pass ownership of this transmit instance over to thread B. And that's going to allow us to communicate between thread A and thread B, or should I say from thread B to thread A. So we can have some data on our thread B, and we can send that with the transmit instance that is now owned by thread B, and we can pass ownership of that data to this send method on the transmit instance, and by doing so, we're effectively putting it in our channel buffer, which our receiving end can then use and get out and consume. So without ado, let's get cracking. We're gonna let our main thread be the consumer thread, just like in our slide right there. And we're gonna get our downstream and upstream instances, which we're gonna name RX and TX, like this, from the MPSC channel function that is brought into scope by standard sync multi-producer single consumer. That's what that stands for right there. We're then going to create our secondary thread, our thread B, by bringing first of all the thread module into scope with standard thread. And then we're going to spawn a new thread. And we need to move, like we talked about in that slide right there, we need to move ownership of the TX instance into our thread so that we can effectively move data from TX into RX like so. So we'll go ahead and define our closure here, and we use the move keyword to move ownership of anything that's captured within our closure here. So we can say, let's pass in something easy. We'll pass in let val equals string from, we'll do hello world, hello threads. I like that. And then we're gonna capture TX, and then we're gonna send that value, and we're gonna unwrap here. And I'll go ahead and close that off there. And I got these mixed up. Silly me. If we run this right now, nothing interesting is going to happen. But under the hood, tx.send will put a reference to our hello threads string into our channel buffer. In other words, data will be sitting in our channel waiting to be received by our consuming thread, which is our main thread in this case. We called unwrap here because our send value here is a result type, if you can see here, result. And the reason that it's a result type is maybe there's a chance that this RX could be out of scope when we're trying to send to the channel. In that case, the channel would be broken and we'd want to error out here. So we'll go ahead and panic if that's the case. To get something out of our channel on our consuming thread, we're going to call rx.receive, recv.unwrap to get our string. This blocks, so if the channel buffer is empty, our main thread will wait here until our worker thread has sent at least one message, which it'll do after it has spawned and started its work. We decide to use unwrap here. We will get an error just like from TX if our channel is broken, basically. If there's no messages within the channel buffer, and there's no TX reference in scope in any of the producing threads, then we will error out here, and we're okay with panicking in this case. But with that aside, we'll go ahead and print out our received message like so, and we'll do cargo run now. Hello threads, whoop-de-doo. That's the basics right there. Nothing too crazy, right? So what's also pretty cool is that this RX, this receive instance right here from our channel implements the iterable trait. So that is, we can keep looping through the buffer of data waiting to be consumed until TX, our transmit instance, goes out of scope. That'll look something like this, and we'll walk through this real quick. So we're spawning a new thread here, and again, we're allowing ourselves to move our captured transmit instance into this thread. We want to possess ownership of it, and we created a vector of strings here, and we're going to send each, this could be like our, from our example, this could be like a session thread on a multi-threaded web server application that maybe is receiving requests from a user, and we want to process these requests in our current logging thread, or our main thread in this case. So we'll go ahead and loop through and then wait a second, and within our main thread here, we're going to iterate through Rx, and once the buffer is empty and there's no more or TX goes out of scope here, that is when our thread is finished, our second thread has finished its work, it'll go ahead and exit down here. So we can, if we really wanted to, we could print out done, just to show that we get out of this iterable. So I'll do cargo run again. And as you can see, we're waiting a second and we're getting all these messages from our producing thread. But wait, you might be screaming, I opened up this video and you showed me multiple producers and a single consumer. And so far we've only gone over a single producer and consumer. Well, it does make sense to step it up a notch now and show an example of a multi-producer single consumer setup. That's in the acronym anyways, multi-producer, single consumer right here. To send from multiple sources to the same receiving end of a channel, we will call clone on our transmit instance here. Clone makes a deep copy of the instance we call it on. We're not going to discuss clone in depth in this video, but you should know that types that implement the clone trait typically reside on the heap, which our transmit instance does indeed, unlike primitives like i32 or car. So we'll step through this example again. We go ahead and spawn a thread up here, and we have, this could be like from our example, this could be thread A. We don't have thread C in this case, so I'll delete thread C, but this will be our thread A with actually multiple data. So we're going to have multiple data from our thread A here. We have a vector high from the thread, and we're doing the same thing. We're slowly trickling out values from our worker thread here. And then we spawn a second thread right after we have created the first one. So again, this doesn't block or anything. And it is worth mentioning, we're capturing our TX value here. And we use different TX values because, again, we cloned it and TX1 is already owned by the first thread we spawned. So we have a copy of TX in memory that we have sent to this first thread here, and then we pass ownership of our original instance here to our second thread. And we're doing the exact same thing, more messages for you. And we're going to iterate again until there's no more TX anymore. So that is when both of these threads that have their respective transmit instances, when TX goes out of scope, that would be at the end of the closure, then that means that the channel is broken and there's no more messages that can be received anymore, and we won't be stuck waiting forever for messages that won't be received. So we'll go ahead and you can pause the video real quick and think what's going to happen. I'll spoil it for you if you didn't pause the video. It's going to more or less zipper between high, more, from messages for you because we spawn these threads at the same time, and since they're at the same time, then we're not going to wait for one thread to completely finish its work. So I'll go ahead and do a cargo run real quick. Make this a little bit bigger. As you can see, we're zippering our way through our produced messages, and we're consuming them by printing them out to our terminal. We can also use receive, or should I say try receive, to not block our consuming thread. Try receive will check if there's any messages in the channel buffer, and if not, continue on its merry way. This might be useful if there's other work the consuming thread can do while it's waiting for messages. As an example, I have modified our current program to count up while it's waiting for messages from our producer thread. So the only difference I made between what you just last saw and now is I went ahead and said, okay, there's some work to be done in this consuming thread. We're adding one, whoop-de-doo, and we're printing out whatever it is, and then we're sleeping for a little bit. Just pretend like we're doing something useful, right? So I'll go ahead and do a cargo run real quick and try to guess what's going to happen here, but should be relatively straightforward. We're going to go ahead and do our work from our consuming thread, and then at the same time, if there's anything in our buffer, we're going to go ahead and print it out, and then we're just going to keep on looping forever. That's it for this video. In a nutshell, we saw how we can pass ownership of values from one or more producer threads to a single consuming thread with the, you guessed it, multi-producer single consumer message type. We used clone to create multiple transmit instances here, which our producer threads can use to send data to our single receiver instance. Do know that this type does not support having multiple receivers on the same channel. Be sure to check out this video's exercises for extra practice. See you in the next one.